me just check. Okay, let me just check if you guys are already in front of your computer. So just give me a thumbs up. All right, so I guess most of you are already here. All right, so here's the shortcut. So here's the best thing that I could teach to you guys. So when it comes to knowing if you are really maximizing the power that's being transferred from your E Thevenins to your R load, okay? So your R Thevenin, okay? So this computed R Thevenin right here should be correct at first, okay? It's not just that you could say that, okay, this is already maximum power transfer theorem. Okay, so this is quite crucial because you have to solve the correct R Thevenin. So once you have that one, then you can now see right away if you are getting the greatest power that's being transferred from your voltage source right here to your R load. So in here, your R Thevenin should be equal to your R load. Okay, that's already the best answer. R Thevenin should be equal to R load. Okay, if they are equal with each other, then oops, where is my one? Then you are now maximizing, or you're getting the maximum power transfer. Okay, only if they are equal. But if they are not equal, then you're not getting the maximum power transfer. So as you guys can see right here, we have these values. So we have this computation for the uh, 0 0.8 ohms for the R Thevenin and then R load. So you will get 39.2 okay, power that's being transferred from your original to your R load right here, in which you will get 39.2. Okay. However, if you're going to let's say decrease okay the R Thevenins from 0.8 to 0.5, okay, you will see right here that you're now only getting a 37.11 uh, watts okay of power. Okay, so for the computation, I would leave this one to you guys since you guys already know how to calculate for the uh, voltage in here, voltage drop, the current right here, the current right here, and so on and so forth. Okay, so in here we have 39.2 and then we have 37.11. And then what will happen if we increase that one from 0.8 to 1.1? Still, we are getting a lesser power transfer. So before we have 39 and then it became 37 and then in here it's now 38.22. Okay, so that's the reason why if we have this R Thevenin equal to your R load okay, values, then that's already the maximum power that you could get from your voltage source. All right. So instead of solving that one by one, okay, using this Pmax right here, okay, and then try to experiment what is the best RTH value right here. Well, uh, you can just see, or you can just take a look just by looking at the RTH value. So if it's super close with the RL, then probably you're getting the maximum power transfer theorem already. I mean, yeah, maximum power transfer already. Okay, but if it's quite far, especially if it's lower, okay, than the RL, then there's a chance that you're not getting the maximum power transfer. All right. So, did you guys get the idea so far on how to identify if you're getting the maximum power transfer? And then how to solve it? Of course, it's already in here. Just use the formula P is equal I times V. Okay, and then you will get the power on that R load itself. Okay, so any questions so far? Are we clear so far?
Yes, sir.
Okay, so that's actually already it. Okay, and then the rest are just the explanation or concept. Okay, so if you were designing a circuit for maximum power dissipation at the load resistance, this theorem would be very useful. That's only if you wanted to get the uh, efficiency of your circuit. Okay, so in here, simply set the load resistance equal to that Thevenin or Norton equivalent or vice versa to ensure the maximum power dissipation at the load. So, this kind of theorem, okay, is super fitting onto radio transmitter, grid tied inverter, electric vehicle design because those kind of let's see, devices wanted to get the maximum power transfer from our voltage source. So you don't want to waste the energy like uh, getting a higher resistance just to be safer with your circuit, just in case there is a fluctuation. So there are some cases that you should match the R load to your R Thevenin. So with that, you'll be able to maximize the sources or the voltage that's coming from your outlet to your specific appliances. All right. And then what else? So the maximum power transfer theorem does not, okay, uh, does not coincide with the maximum efficiency. Okay, so application of the maximum transfer theorem to AC power distribution will not result in maximum or even high efficiency. So, well, it only work if your circuit itself is an amplifier, like it's amplifying the 10 volts to 20 volts, okay, with the use of a certain components, of course. And then what else? So, nothing that much important in here. And then the maximum power transfer theorem states that the maximum amount of power will be dissipated by a load resistance if it's equal to the Thevenin or Norton resistance of the network supplying the power. So the maximum power transfer theorem does not satisfy the goal of maximum efficiency. Right? And then here's the reference for this one. So this one also came from All About Circuits. And for the other related articles, you can visit electronic tutorials or tutorials point. Right? And then for the sample videos, you can visit those. And then for a Tagalog tutorial, you can visit this one. All right. So I guess if you already know how to solve Thevenin's theorem, then you're good to go. Okay, because what we did in here is just by simply solving a Thevenin's equivalent, and then solving for the uh, voltage drop, the current, and then the power. Okay, and so on and so forth. So yeah, and then just by looking at the R-Thevenin itself, you already know that if it's really maximizing or you're maximizing the power that's being transferred from your source into your R load. So yeah, that's it for this module. So any questions so far? Any questions or clarifications? So we have plenty of time since these last two modules are actually super easy and simple. So again, you will now only have one more quiz. So you will not be having a quiz for the Millman's and then the maximum power transfer theorem anymore. Okay. So you're going to have one more quiz, which is the delta to y or y to delta transformation. Okay. So just that, and also we will not meet anymore for this coming uh, Monday. All right. It's coming June 14th. So I'll give that one as your free time to finish all of the activities which I'll be giving to you. Okay. And then your final exam will be on Thursday. Okay. Because the start of exam is 16, 17, and 18. So your final exam will be on June 17th. Okay. Thursday next week. And of course, the coverage of your final exam. So I'm actually thinking if I will not include Millman's theorem anymore, or I will just combine it with the other theorem. Because in one of my number, of your exam, I combined the Nortons and Thevenins. Okay, I did combine them. So one original circuit, and then you will transform that one into Thevenin, and then transform that one into Norton. So I'm not sure yet if I will remove some theorem, but just to be sure, just review everything. Okay, from the start up to the end. So the last 6 modules. So those are the Thevenins up to maximum power transfer theorem. Okay, so that's basically the coverage of your final exam. Okay, so any other questions so far for clarification? Okay, so I guess none. All right, so if you don't have a question anymore, so just give me a thumbs up, and then after that, you may now go. But if you have a question, so feel free to message me, and then good luck to your final exam. All right, okay then. So you guys may now go if you don't have a question anymore. So to those who will leave now, so good luck. And then to those who have a question, so feel free to ask me that question of yours right now, so we can talk and we can make a remedy of your problem.
Whether
Goodbye.